Ripple Tank at School, Part 2, Interference Patterns. We have here the point source, the second point source, and they're sending out waves. They form circles that overlap. When they overlap, they form interference patterns. This is a screenshot from the video of the lab I did at school in our wavelength. The bright rings represent the crests, and the dark spaces in between are the troughs. Here we can see a crest from this source and a crest from the other source formed an intersection right here. Well, when a crest gets on top of a crest, we have a larger crest. Now we can see right here, we have a trough on top of a trough, one from each source. Here we have a crest on top of a crest, a trough on top of a trough, and another crest on top of a crest, trough on top of trough. Along this line, the two sources form a maximum. This is where the wave amplitude will be the biggest. This is right in the middle of the diagram, and we'll call this the principal maximum. Count the number of waves from this source. 1, 2, 3, 4. Now count the number of waves from this source. 1, 2, 3, 4. It only makes sense that they're going to match up because they have to travel the same distance. So there's going to be 4 waves and 4 waves. The difference is 0. Let's look at this intersection up here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The difference is the same. There's symmetry here. This is right down the middle, and it's the same distance from each source. Now let's look a little over to the side, and we can see that there's an intersection right here. This is a crest from the source on the right. This is a crest from the source on the left. And that's a crest on a crest, making a large crest. We move outward, we have trough on trough, crest on crest, trough on trough, trough on trough, crest on crest. We have another line here where we have a very strong wave pattern. This we call the first maximum. Take a look at the number of waves from this source to this intersection, and the number of waves from this source to the intersection. We have 1, 2, 3, 4. 1, 2, 3, 4, 5. There's a difference of 1 wave. And because that difference is 1 full wave, we get an intersection of crest on crest, trough on trough, crest on crest as we move outward. There's always going to be a difference of 1 full wave along the first maximum. And if we move over a little further, we're going to find more intersections of crest on crest, trough on trough, crest on crest, trough on trough, crest on crest. And that line will be called the second maximum. Let's count the number of waves from each source to an intersection. We have 1, 2, 3, 4, 5. 1, 2, 3. The difference is 2 waves. So when we don't have a difference at all, it's the principal maximum. When we have a difference of 1 wave, we're at the first maximum. When we have a difference of 2 waves, we're at the second maximum, and so on. Now you might notice in between the principal maximum and the first maximum is a line of blurriness. And we're going to count the number of waves from each source to this point here. Looks like we have 1, 2, 3, 4. This is the crest from the right source. And we have 1, 2, 3 and a half. Here's the third wave, there's the fourth wave. Well, here we're off by half a wave. Well, what would happen if a crest got here when a trough got here from the other source? They're going to cancel out. That's what's going to happen all along this line. And this line is called a nodal line. Everywhere on this line, the crest will meet with trough. We're going to have the same thing happen here too. That would be another nodal line. Let's count the number of waves. Let's count the number of waves from each source. We have 1, 2, 3, 4, 5. And from here, 1, 2, 3.5. We didn't make it out to the next wave. So it's 3.5 and 5. We're off by 1.5 waves. So every time we're off by multiples of half waves, we're going to get cancellations, and we're going to have a minimum along here known as a nodal line. And we'll have another nodal line here. So the pattern just keeps repeating itself as you move outward from the principal maximum on either side. Now this diagram is taken at a bit of an angle. We need to look head on and draw a separate diagram to make things clear. Keep in mind that in real life, this diagram is representing something that's moving. These waves keep on moving outward. And you can actually see these lines if you look closely in the video. Here we can see in this computer simulation, two sources, and the waves are moving outward. The white lines represent the crests. The space in between represents the troughs. This is the principal maximum. You can see where the crests are intersecting all along that line. We've paused it just as a wave forms, and we're going to count out to say this intersection. 1, 2, 3 waves. We can do the same from this one. 1, 2, 3 waves. It's the same distance, it's the same number of waves all along that line. Now we can look at the first maximum. We'll count to that intersection right there. 1, 2, 3. 1, 2, 3, 4. The difference is 1 wave. Now we'll look at the second maximum. We'll count the waves to this intersection. 1, 2, 3. 1, 2, 3, 4, 5. The difference is 2 waves, and that's the second maximum. Now, what line do I have here? There seems to be no intersections. Let's take a look at this point right here. We have 1, 2, 3 waves and 1, 2, 3.5. We have the trough from one source intersecting with the crest from the other source. Everywhere along this line, crest and trough are intersecting from each source, canceling out. This is the nodal line. That is the first nodal line. Here's a second nodal line. It's where the water would be all calm. Now the pattern can change depending on a few things. For example, the distance between the sources. If I move them closer together, I have less maximums and less nodal lines. That's quite evident when I put them on top of each other. The wavelength will affect the pattern as well. I'm making the waves longer now. What we need to do now is derive some math so we can use the pattern to calculate the wavelength. Here we have two sources. We can measure the distance between them. I've drawn in the principal maximum. This is the line along which the distance from each source will be the same. L1 and L2 are equal. I'm only going to draw in a small section of each crest, and I get 1, 2, 3, 4, 5 waves along that distance. Well, I'll get 5 waves along the other distance as well. So the crests will meet up on top of crests along the principal maximum. Now imagine I look to the right of the principal maximum and I find a point where I have yet another maximum. I'll find that L2 is bigger than L1. I find I have 1, 2, 3, 4, 5 waves along L1. And I have 1, 2, 3, 4, 5, 6 waves along L2. The difference of L2 minus L1 is 1 wavelength. Wherever this occurs, it's the first maximum. And that would be all along this line. If we were along the principal maximum, the difference would be 0 waves. And if we went further out, we would find a line along which the difference would be 2 waves. We'd now be at the second maximum, and so on. There could be a third maximum, a fourth maximum. Now imagine I take L1 and I swing it over to here. What would be that distance? If we're at the first maximum, it would have to be 1 wavelength. By drawing in this line, I now have an isosceles triangle up here. If we're far away on the first maximum, the isosceles triangle will have sides that will become perpendicular to this base. This is an approximation to make it a 90-degree angle. It's an approximation that gets better as we move further away on that first maximum. We can measure the angle between the principal maximum and the first maximum and find that angle somewhere in here. Did you guess that it'll be there? Now that really is a 90-degree angle. And you can do some geometry and prove it, or just rotate a sheet of paper. The principal maximum is 90 degrees to the distance between the two sources. If I rotate the paper over to the first maximum, I will have rotated the same amount above this distance. Well, we can make that an approximate 90-degree angle as well, and then we have a right triangle. How would you calculate that wavelength given theta and d? D is a hypotenuse. We can say d sine theta is this wavelength. And it's only going to be 1 wave if we're at the first maximum. What do you think it's going to be if we were at the second maximum? The difference would be 2 waves. And it would be 3 if we were at the third. So how could we generalize this? We'll put in the letter n to represent the first, second, third, etc. maximum. And so here's your formula that you can use to calculate the wavelength using an interference pattern. Now, using the data from the actual lab at school in the wavelength, we had 10 degrees approximately from the principal maximum to the first maximum and 18 centimeters between the two sources. Now we'll use d sine theta equals n lambda. We're going to use 1 because we were at the first maximum. We get 3.13 centimeters for the wavelength. Going to the second maximum, we have an angle of about 20 degrees. We're at the second maximum, so we're using a 2. Now we've calculated 3.08 centimeters for the wavelength. They're pretty close. Well, we can check this with what we got for the velocity equals frequency times wavelength part of that lab in the last analysis. Using the meter stick and counting the frames, we measured 37.5 centimeters per second. The oscillating machine told us the oscillating machine gave a frequency of 12 hertz. And we can calculate the wavelength. And we get 3.13 centimeters. Man, are we on the money. And we even have one more way. We were able to pause the video and we counted 10 waves in a distance of 30 centimeters marked along the meter stick. And that gave a wavelength of 3 centimeters. So both of these measurements check out with the formula for the interference pattern. Now you need to go practice all this on the worksheet.